And hello, welcome to this video. So in this video, last time we talked about the Peng-Robinson equation of state. Yeah, and we were trying to calculate pressure. Now we don't even know if the pressure of the Peng-Robinson equation of state, does it make sense? Okay, we were writing the code. And yes, we did write the code, but we don't know whether the pressure we are calculating is correct. So that's what we want to test in this video. And I want to elaborate more about tests anyhow. So basically, the idea of tests are to verify that the code is working correctly, right? So imagine you have this function here. Generally speaking, before you start coding other things, you want to put a test. What if you don't put a test there and you continue coding? Now, if you continue coding and you use your Peng-Robinson equation of state equations without testing, and suddenly, or not suddenly, over time you build several layers of code. Maybe this Peng-Robinson equation of gas, equation of state is used for some sort of a compressor or turbine code, or even a aeroplane wing, or I don't know, somewhat of those equations where you deal with compressible flow. Okay, and then somehow you run into a bug. If you didn't test all your code before, you would have to look through every single bit of code you wrote. Let's say you wrote 10,000 lines of code. You would have to find your bug in that 10,000 line of code. Okay, maybe you have some debuggers to help you, right? So if you don't want to, get yourself into that trouble, finding one single bug in 10,000 lines of code can cause quite a fair bit of headache, especially if that 10,000 lines of code is spread out over 10 or 20 files. Okay, this is what happens when your project goes big. Yeah, and definitely that's like a really big headache. Yeah, so from experience, or rather, if you want to avoid the headache, yeah, please write tests. Okay, write unit tests. This is very important. Okay, so been through sort of enough pain to tell you, yes, tests are almost absolutely essential almost all the time, especially if you write big programs. Okay, but if you don't believe me, go and try it out yourself. Try coding without tests. Try doing it quick and so-called quick and dirty. Yeah, you see whether you can live with it, or you would think later that writing tests is better. Okay, so anyway, yeah, what I'm going to do is I'm going to use Wolfram Alpha's Peng-Robinson equation of state. Okay, if you type Peng-Robinson equation of state in Wolfram Alpha, you will be able to calculate various things. For example, the pressure, molar volume, or temperature. And you'll just put in some parameters, okay, like eccentric factor, critical pressure, critical temperature, so on and so forth. And you'll be able to calculate pressure. Now, let's say we want the carbon dioxide, Peng-Robinson. Okay, let's see a carbon dioxide Peng-Robinson equation of state. Yeah, or rather, let's look for the eccentricity factor. Okay, no, what? Let me go and quickly get it for you. Okay, so we have it from this website. Okay, I just did a quick Google search and here we are. Of course, you can look at Wikipedia as well, or even this Science Direct. You'll be able to find critical temperature and pressure. Okay, let's see whether I can find the eccentricity factor here. Or not here. Let's see. No, I can't find it. Not here anyway. Closest is this one, critical constant and acentric factor. Okay, let's see, acentric. I can't find it. Acentric factor, this is the omega I'm looking for. Scroll down a little bit and you'll see carbon dioxide. Okay, critical temperature is 304K, so I'm gonna put that right here. 304K, 304. What's this? 73.8 bar. All right, 73.8 bar. 73.8 bar. Okay, and what's the eccentricity factor? 0.239. Okay, 0.239 is the eccentricity factor. Put this here. And then molar volume and temperature. Okay, I'll put this 304. Okay, and this will be, I guess, no, I'm going to put it sort of a subcritical. Maybe let's put 250. Okay, let's compute. So according to Wolfram alpha, the Peng-Robinson equation of state would yield a pressure of, what is this? 0.8303 atmospheres, or 84.183.9 pascals. So, right, so this is our molar volume, this is our temperature, this is our critical pressure, temperature, pressure, and eccentric factor. Now let's try putting it into this function right here, and let's see what happens. Now, I'm going to do it the normal way. Yeah, I'm going to do it the normal way that assumes that we are not going to use the specific code meant for writing tests in Rust. Okay, the naive way is as so. Let CO2 pressure equals to Peng-Robinson. Okay, I'm going to use the get pressure. Okay, and I'm going to write all of this here. Of course, I'm going to get errors because I don't have the temperature, volume, pressure, so on and so forth. So let's just type in all of those. Temperature will be thermotemp. Okay. New. I want to okay, pardon me. Let me import all the necessary components for UOM in float 64. Okay, I'll put a thermodynamic temperature here. I will need to use the new function, or the, what do you call that, the new associated function. So it will be a Kelvin unit. Let's see, quick fix, I'll import Kelvin, thermodynamic temperature Kelvin. Let's do the molar volume as well. Molar volume, new mole per meter cube, cubic meter. Okay, cubic meter. Yeah, that's the one. Okay, oh, this is liter per mole. Liter per mole. So it's molar volume. So cubic meter per mole. That's the correct one. What's the correct amount? 24.5. Okay, this one is in liters per mole. Pardon me. Liters per mole. Let's do liters per mole here. Okay, looks like Liter. No. Decimeter. Let me go and find the unit. It's a little hard to find right now. Let me find it. Okay, so 1 liter is about 1 dm cubed. So I'm going to use the unit cubic decimeter per mole. This is 24.5. Eccentricity factor is a ratio, 0.239. Ratio, new, ratio 0.239. Okay, I'm going to import the unit. Okay, just getting used to VS Code. Let's put the critical pressure here. Pressure, new. Okay, what's the unit? The unit here is bar. I'm going to use bar. And what's the bar? 73.9. Let's see whether I got it right. 73.8. Okay, let me correct that. 73.8. What's the critical temperature? It will be 304 K. Okay. Thermal temp, new, Kelvin, 304.0, thereabout. Okay, so nice thing about VS Code is that it will auto sort of tell you what these variables are in line. Okay, there's a setting you can change for that. It doesn't always come naturally. So do take note that you can do this sort of thing. Okay, so let's debug the CO2 pressure. And let's check what the pressure is manually. Okay, if we take a look over here, the pressure here is 84.8. Okay, so this is in SI units, this is Pascal, or rather 84,000, thereabout. So what do we have here? Okay, we're about 84183.9 pascals. Okay, so 84178.9. Oh, pretty close. Okay, pretty close if you think about it. This is less than 1% error. Okay, so yes, this is the naive way of doing tests. This is pretty manual. Okay, you can sort of tell that, hey, the pressure here is 84,000 pascals, which matches pretty closely with what Wolfram is doing. Okay, when we actually put in all the correct parameters, okay, it matches pretty well. So by and large, our Peng-Robinson equation of state is seemingly working not too bad. Okay, not too bad. So yeah. So is there an more efficient way to do this, right? If we want to test for many gases, many types of gases, then we are gonna have some problems, you know, if you want to like so-called automate things. Okay, so yeah, there is a way, and there's a better way to do things. We want to talk about the assert crate. Okay? In fact, I want to use the Approx assert crate. Okay, Approx assert equal for Rust. This is a very useful crate. Okay, so it allows us to check whether two numbers are equal. Okay, so what this does is that what this crate does is that it allows us to check whether two numbers are equal. So or at least equal to some certain bound. Now for engineering cases, we do not need 100% agreement. So the gap pressure Peng-Robinson gas doesn't have to agree 100% with what is actually given in here in Wolfram, but the closest thing is maybe within 1% or 0.5% difference, you can still agree. Yeah, if that's good enough, then hey, why not? Okay, then you should sort of pass. If you don't pass it, then we will fail the test, so to speak, or it will throw some kind of error. So this is the whole idea of tests. All right. So let me just demonstrate one time for you, that so that you can do it. Okay. First thing first. We will need to import our crate first. Okay. So we do need to take a look at our cargo.toml. Okay, we do not have any other dependencies other than CSV and UOM at the moment. Next, if we want to use this Approx crate to help us check whether this CO2 pressure is equal to, this what's over here. Okay, 84,183.9 pascals. If you want to do that, then we can import the Approx crate. So cargo add Approx, that's how you add the crate. Okay, and we go cargo watch X run again. All right, so okay, let's put the reference CO2 pressure here. CO2 pressure, and this is what the one in Wolfram is. Okay, so I'm going to just copy and paste this number here. Oh, I can't really copy and paste. 84183. Okay, 5 significance figures may be enough. 84183. And I'll put a 0.0. Okay, it's a 0.9. Never mind. I just typed everything out. Okay, 84183.9. So let's see. Yeah, this should work. Okay, except that there is a warning right here. Maybe pascals is not so-called imported. Okay, there's no Pascal in this scope. Okay, I'm going to hover over to try and have a quick fix. Yeah, it says consider importing this UOM SI pressure Pascal. And I'm going to do just that. Okay, use UOM SI pressure Pascal. Okay, I don't know why the quick fix isn't working, but this will fix everything. Okay, so now we have this. Now, if we actually do a debug macro, and we use the reference CO2 pressure, we should be able to see both of them pretty similar. Okay. Okay, so take a look here. Yeah, you see this this pressure here, CO2 pressure is this much. The reference CO2 pressure from Wolfram is this much. So I'm going to change this to make sure it's oops. I'm going to change this to rename it such that, hey, I want to so-called ensure that you know it's from Wolfram. So I'm going to use the rename function, and okay, Wolfram, yeah, reference CO2 pressure from Wolfram. Okay, and now I'm going to use the assert relative equal. Okay, assert relative equal, just to show you how things are done. Okay. Okay, I do not see any. Okay, maybe let me take a look at the assert relative equal. Yeah, assert relative equal is here. Yeah, this is the function we use. Let's try just doing this. Okay, assert relative equal CO2 pressure and reference CO2 pressure Wolfram. Of course, we need to give it an error bound, but we'll do that later. Okay, of course, and then we have some error here because they can't find the macro in this scope. So to import the macro, we need to use the macro use keyword and extern create approx. So this is how you import the assert relative equal macro. So I'm just going to copy and paste this and put it on top of here. So this is going to help us to check whether two things are equal. Okay. Now we see that the relative equal is not implemented for these two things. Yeah, they are not implemented for quantity. All right. In fact, these are quantities and they are not implemented. So one workaround, of course, is to use the value attribute. Okay, or actually better still, use the get attribute. Yeah, so I'm getting the float value in pascals. So this seems to work a little better in general. So what this does is to convert the CO2 pressure, and I'll just get the number in pascals. Okay. All right. And then I will compare these two values which are in pascals. So again, I have the CO2 pressure from my Peng-Robinson gas. I want to compare it to Wolfram automatically using code. So what I do is to hard code the Wolfram value that we saw just now. And then I want to compare it with the CO2 pressure. To do so, I use the assert relative equal macro. The macro is the one with the bang sign or exclamation mark. And to do that, I use this extern create approx, and I use this macro use. Most of it is just copy and paste based on the example here. Okay, so next thing is I'll need to actually give some error bound. Okay, because when I actually use this assert relative equal, assert relative equal actually panics. Okay, so this code is working correctly. Okay, why is it working correctly? Because your left pressure is this much, 84178.9, and the pressure on the right, which is this Wolfram pressure, is 84183.9. So we are getting both pressures in pascals. We are passing, and we get it back as a float, which we float F64s are things we can compare. The units themselves, we may not be able to compare them as you saw just now, but that's okay. We can just get the float values and make sure they are in the same units before we compare them. Okay. Now, obviously these two values are not exactly equal, but they are approximately equal. How do you tell the assert relative equal macro how much is good enough? Okay, so we can use the thing called max relative equals to maybe 0.01. So this gives you the maximum percentage difference between these two. Okay, once you do that, this test, so to speak, will pass. So this is the assert kind of thing. If I put max relative is 0, I'm gonna get the same error again. Threat panicked. Okay, because this 0.0 it means that hey, if there's even 1% of difference or 0.1% of difference, this code is going to throw an error, or in other words, panic. So if you don't want that, if let's say I want to agree within 1%, I will use max relative equals to 0.01. This just checks whether both of them agree to be within 1%. If you want 0.01%, then just do this. You add another 0 there. It should still work. Okay, because these two actually match pretty close. Okay, now that's done, I can just remove these two debugs, and technically, if nothing goes wrong, then the test that we run is not going to give us any issue. That's ideally the way we want to run tests. Okay, so I've talked about so-called the basic idea of constructing tests. Okay, we actually want to test our function to maybe get the pressure of carbon dioxide at some molar volume and pressure. Okay, so I supply all of these factors and I compare it against an existing code or an existing reference, which is Wolfram alpha. Okay, by and large, pretty reliable. So if my idea is that if it is comparable with Wolfram alpha, then okay, good. Okay, to automate this process, I use this assert relative equal. Okay, however, most of the time you do not want to well, let me not jump steps. Okay, when you do your programming, you're often going to get 10-20 functions at least if you're going to code a relatively big program. Okay, a big library, a big program. Okay, like the likely thing is that you want to keep your tests well organized. Okay, you want to keep your tests well organized. So what can we do to keep our tests well organized? Okay, so instead of just putting all of this into our functions, we can actually create a function and solely run it as a test. How is that done? Okay, the syntax is as follows. You just use the # test, # with test, and you put you code a function as per normal. So I'll call this function the CO2 test. Okay, the CO2 test. I'll save this first because that's not going to do anything. Okay, what I'm going to do is I'm going to instead of cargo watch-x run, I'm going to use cargo watch-x test. Okay, so what this does is that it will just run one test. Okay, this is the CO2 test that will run if we use the cargo watch-x test. You will notice that none of the code in the main function is used. None of the code in the main function is used. All right, so if we want to make sure it works properly, our test works properly, we will need to use the test # here, and then just do the create a function as per normal. So I call this function the CO2 test. Okay, CO2 test. Maybe let's give it a better name. Test CO2 pressure Peng-Robinson subcritical. Okay, so this is a very descriptive way of test, and you take a look here. When you run the cargo watch-x test or cargo test, you will be able to see that this test is run. Okay, and then it says this test is okay. Okay, the thing is that when you have this test is okay, you'll be kind of sure that the test here actually runs to completion. Okay, without an issue. Now let's actually put the test code in where it's supposed to be. I'm going to put it into our test right here, and it will still pass because this code actually passed, right? Now let's say, yeah, how can we get this no, maybe I'm jumping too many steps again, pardon me. Okay, so this test passed because the CO2 pressure here is roughly the same as the reference CO2 pressure here. So the moment we try to assert relative equal, everything turns out fine, and we so-called pass the test. Now if the test doesn't pass, and let's say this CO2 pressure and the reference CO2 pressure is not close enough, okay, so let me simulate that by just using a max relative of 0. Okay, the test will fail. As you can see, the test fails if these two are not, close enough in value. Okay, that's because I of course reduce the error bound to 0. Okay, so that well, we have no tolerance for error. But if we can tolerate 1% or 0.1% of error, then the test will pass. Okay, but the nice thing about tests is that it will tell you which test has failed. For example, test CO2 Peng-Robinson subcritical. This test has failed. Okay, and what the cargo test actually helps you do is to identify which exact test functions have failed, so that you can kind of pinpoint where your errors are. That's the very useful thing about tests. Okay, so for a good practice, in fact, is that every function you code, or at least every major function you code, that is error prone, you don't know whether it's correct, you'll tend to want to perform unit tests on them. Okay, and of course, name your unit tests well so that if you have 100 tests over here and some of them fail, some of them pass, you'll be able to see which one of them actually fails. So use good naming convention. I'm pretty sure there are plenty more resources online. You can go and take a look at it yourself, but I just want to tell you what tests are and how to code them in Rust. Okay. So again, let's say something goes wrong. Okay, I'm going to save this. Let's say something goes wrong and yeah, let's say something you code something wrong with the test, and let's say I'll just type plus 2.0 here. Right, this test will fail. Okay, this test will fail. Okay, you can see that the pressure in the left hand side is not equal to the pressure on the right hand side. So the right hand side, this one is actually our reference pressure, and this is our test pressure. So this is, I'm just simulating a bug, but you can see here that if you use the test macro or the test attribute, we will be able to pinpoint our tests really quickly. Okay, and this is how you do it. So so by and large, make sure that please write tests. They are very useful. Okay, so this is the way we check to see if our code has been done correctly. Okay, and if the test passed, then you know that this function is sort of done correctly. And when you kind of test that this function is done correctly, you don't really have to bother with this function ever again. And if you run into bugs that sort of if you run into bugs with a big program and the big program happens to use this function, well, you don't have to worry about it because you tested it before. Now, of course, you have to make sure you test it thoroughly, but at least test it. Yeah, test it. So these are best practices that industry uses. Always put plenty of unit tests. Okay, so make sure you do that when you do your simulation program. Okay, by using this test function right here. So I'm going to stop now. I hope this was helpful for you to understand a little bit about testing, verification, and so on and so forth. Okay, so I'm going to stop. See you.